Welcome back, everyone, to this discussion on lasso regression, that is L1 regularization. Recall that L1 regularization adds a penalty term equal to the absolute value of the magnitude of the coefficients. We can see here that in general it's very similar to ridge regression, except instead of considering the squared coefficient, we're just considering the absolute value. So what's the main change there? Well, in general, this limits the size of the coefficients. That's not too different than what ridge regression did. However, the most important difference and the key qualifier of L1 regularization is that it can yield sparse models where some coefficients can actually become zero. Lasso can force some of the coefficient estimates to be exactly equal to zero when the tuning parameter lambda is sufficiently large. Similar to subset selection, what the lasso regression can do is actually perform something very similar to variable selection, because if you set some coefficients equal to zero, that means you're not even considering that particular feature. So that allows models generated from the lasso to be generally much easier to interpret. Keep in mind when it comes to actually performing lasso regression with scikit-learn, the lasso CV model we're going to be using operates on checking a number of alphas within a range instead of providing the alphas directly. And we'll actually touch more on that later on in this lecture. So let's explore the results of a lasso regression in Python and scikit-learn. Okay, here we are at the Jupyter Notebook where we left off last time. As a quick note, you may see lasso fully capitalized sometimes because it's actually an acronym for least absolute shrinkage and selection operator. So just a quick note on that, although it's very common to just say lasso with just all lowercase letters as well. Let's go ahead and take a quick exploration of the model we will be importing. We're going to say from sklearn the linear model import, and we have a couple of options here. If I wanted to, I could just import lasso, and then this is really similar to just importing ridge by itself, where you're going to say lasso, and then, capital lasso. And then you would have to provide some distinct alpha value. Recall, this alpha value is technically, if we look back at our equations, that lambda tuning hyperparameter. Realistically though, it's not too convenient to have to know the correct alpha beforehand. So instead, we perform cross-validation in order to figure out the best tunable hyperparameter. And this is where lasso CV is going to be slightly different than ridge CV as far as providing the alpha values. If we take a look at the documentation for sklearn.linear model lasso CV, there's two different ways of figuring out that best alpha tunable parameter. One way is to do the same thing we did last time, which is just provide that list of alphas. So there is this optional parameter, alphas, where you're just going to provide the array. However, if you keep it as none, the alphas are set automatically. And the way that works is it uses this epsilon and n underscore alphas parameter. So what does that actually mean? Well, EPS, or this epsilon argument, essentially is a ratio between the minimum alpha value divided by the alpha maximum value. And then what you do is really similar to np.linspace, that linear spacing, in which it's going to check a number of alphas along the regularization path, where the regularization path is defined by alpha min divided by alpha max. As a quick note, if you check out the user guide here linked in sklearn.linearmodel.lassocv, this will take you to linear models 1.13 in lasso, and eventually it just discusses basic lasso, but there's actually different types of lasso to consider, and there's different types of cross-validation lasso models to consider. There's a more advanced lasso Lars CV as well that's based on the least angle regression algorithm. And some of these more complex lasso models are kind of outside the scope of the course, but you should be able to use them if you go through this particular lecture. So lasso CV, I think, is the simplest one to understand. The other ones are essentially just different ways of tuning that hyperparameter. So there's something called a AIC, or information criterion. There's also Bayes information criterion, which is kind of punishing really complex models. It's kind of another layer of regularization on top of that, essentially what criteria you're using to select the best model. And scikit-learn has methods associated with that. For our case though, we're going to go kind of the simpler cross-validation, which is lasso CV, which should be more than enough for our particular use case. But I do want you to be aware that there is lasso Lars CV and lasso Lars IC for information criteria-based models, as well as kind of more complex least angle regression models available to you. So just wanted to point that out, but let's go ahead and use the kind of base case of lasso CV, where we're going to define the length of path here of alpha min divided by alpha max, and then number of alphas. And for the most part, these default values are actually quite reasonable. So let's go ahead and use those. So we'll say our lasso CV model is equal to lasso CV. And while I do intend to use all the default parameters, I'm just going to explicitly show them here for the case of understanding and displaying everything. So I'm going to say epsilon, which is the ratio of alpha min to alpha max, is equal to the default value. Whoops, let's go ahead and not repeat EPS. And then what I'm also going to say is the number of alphas I want to check is the same as 100. Obviously, if you increase this number of alphas, then you're going to end up checking more and more alphas, which means this is going to take longer to run. And also, the ratio here between the minimum value for the maximum value, as this gets smaller, that means you're checking a larger and larger subset of possible values. So you have to also consider that. And then finally, what you can also do is specify, if you scroll down here, the CV number, which is the number of folds in k-fold cross-validation. By default, if you scroll down in the documentation, it eventually tells you that it's going to say it's a default 5-fold cross-validation. So we'll keep the default. If you want, you can define it here as CV is equal to 5. But for our use case, this should be enough. So let's run it with the default values. You'll notice we've created the model. Now it's time to actually fit the model. So we'll say lasso CV model fit, and we're going to fit it to the X training data and the Y training data. And what it's going to do is going to check a bunch of those alpha values. Okay, so a quick note, you see here there's a convergence warning. And this warning is actually a really common warning. It's essentially saying that that stochastic search for the best alpha value never actually converged. And there's many ways to fix this. If we take a look back at the documentation for lasso CV, you'll notice that there's this max iterations. So it's essentially only allowing this stochastic search for the best alpha value to run 1,000 times. That means if we increase the maximum possible iterations, we can increase the likelihood that it converges. So let's go ahead and try that and see if it fixes the issue. So by default, it's 1,000. Let's go ahead and make it way higher just to see if that gets rid of this warning, to make sure our understanding of the warning is correct. So we'll say max iterations. Instead of only allowing 1,000 iterations for this search of the best alpha value, we'll go ahead and say something like, in this case, 1,000,000 max iterations. And now when we run this, and the fit, you'll notice it fit just fine. Another way to potentially fix this is to try to minimize the actual search parameters. Recall that the smaller this epsilon value is, that means the wider range you're checking. So what we could do as well is keep the default max iterations, but just lower this epsilon search to something like 0.1, so that the minimum and maximum ratio is a little smaller, so we're not searching as wide. So if you run this instead, you'll notice that also works. There's also the capability to play around the tolerance level in case you get that warning. As a note, it is just a warning. It is not a full error saying your model is completely broken. It's up to you which methods you want to use in order to fix that potential warning. You can either not search as wide or just allow yourself more iterations in the search. Obviously, this is kind of a trade-off for really large data sets where the computational time is going to take a while. In our case, you could see that it was quite fast, so either approach is totally okay. For right now, let's not worry about max iterations, and let's actually go with the approach of not searching a huge range of alpha values. Instead, we'll keep the ratio from the min divided by the max as 0.1, checking 100 alpha values there with a cross-validation of 5. So I'll just rerun these again. We can see here there was no warning, so we're good to go there. And now let's check out the alpha value that it actually got. So if we say lasso CV model, you'll notice that we can say alpha underscore to get that particular alpha value. Recall this is the lambda being multiplied by the absolute value of that coefficient set. And then we get 0.494, etc. This is obviously a really long float, unlike before, because it's searching through this kind of in numerical linear spacing. Okay, so we now have lasso CV model.alpha. Let's actually run our test predictions and compare our values. We're going to say test predictions is equal to lasso CV model predict off of X test, run that, and let's grab the test predictions. We've already written this code a bunch of times, so I can scroll back up here and then grab the mean absolute error for the test predictions, run that, and I can do the same thing for the root mean squared error. I can do this copy paste because I'm calling them test predictions every time. And let's check out the mean absolute error. It's 0.65, and the root mean squared error was 1.13. So in this particular case, we can see that lasso, given the restraints that we put on n alphas and epsilon, and compare those results to just L2 regularization of ridge, is actually not performing as good as this other model. So it looks like in our particular case, for these parameter values, lasso is not performing as well as ridge regression. So what benefit do we have from lasso? I think it'll be more clear if we actually check out the coefficients to our lasso CV model. Take a look at the coefficients here, and you'll notice the vast majority of them are actually 0. And that means it's only considering 2 features. Everything else it's not even considering. So that actually makes its performance quite impressive. It's able to get a reasonable mean absolute error and a reasonable root mean squared error by only considering 2 of the features. So the fact that it's performing worse is understandable because up here we saw ridge regression is considering every single feature. So that means the model is much more complex and harder to interpret. I'd have to interpret every single one of these coefficients compared against a polynomial feature set. What's really cool about lasso is that since it allowed a lot of these coefficients to go to 0, I can easily interpret this model. I know that it's only considering this first feature value and then this 5th feature value. And those are the only features I should really be concerned about. Which means later on, depending on what the context of the problem I'm trying to solve is, maybe I only want to collect 2 features. And most likely, it just happens to be the radio and TV feature set. And maybe those were the only 2 features I ever really needed to consider. Now keep in mind, this did come at the cost of a slightly worse performing model when it comes to mean absolute error and root mean squared error. But now the model is way easier to interpret by just considering 2 features instead of the entire polynomial feature set. It's up to you whether this trade-off is worth it in the context of the problem you're trying to solve. But it's pretty impressive that it's able to perform pretty well considering it's only looking at 2 features for its performance metrics. All right, so that's pretty much it for lasso. As we already mentioned, if you want, you can continue trying to work on this and get an even better lasso model by adjusting the epsilons you're considering. And then if you want, you can just say max iterations is much higher, like 1 million or something like that, and run this. And if you want, then you can check out the alpha values that it's doing. So you notice now alpha is actually really small. And when you run these again, the mean absolute error and root mean squared error perform much better. So you give it more time to search for those better alpha values. And now if you take a look at the coefficients, you're getting a slightly more complex model. A lot of them are still actually 0, but it's now considering more. So as you search for more alpha values, what's going to happen is it's going to consider more coefficients as it starts to tune to a slightly more complex model. And then you're still getting the benefit of not considering every single feature with the performance boost from regularization. So now we're getting a mean absolute error of 0.43, root mean squared error of 0.6. If we compare this to ridge regression itself, it's much more in line with ridge regression. So we can see here it's kind of a slightly better version of ridge because ridge had to, in order to get almost the same performance, 0.4 and 0.6, had to consider every single feature. And in this case, we were able to drop almost half of all those features and yet still get almost the exact same performance. So keep in mind, you can also expand the search here for the best possible lasso by adding in more feature coefficients and then getting a better performance model. It all depends on the trade-off you're willing to make between how complex your model is versus model performance and how well you're going to interpret your model. Okay. Finally, let's go ahead and move on in the next lecture to discussing ElasticNet that tries to combine the best of both worlds for ridge and lasso by combining them together. I'll see you there.